Okay, welcome back. This time we have problem of proving this inequality. We have three variables x, y, and z non-negative. We must prove that square root of x cubed plus y cubed plus 1 and then plus square root of z cubed plus y cubed plus 1 plus square root of x cubed plus z cubed plus 1 is bigger than or equal to 2 plus square root of twice of the sum of cubes plus 1. Now this inequality is not easy to be solved using well-known inequalities such as AMGM or Cauchy-Schwarz. I haven't found such a proof, but in this video I will show two solutions. The first one just involves algebraic manipulation, and the second one is using the Karamatha's inequality. Okay, so let us start by the first solution. I will start by rewriting the right hand side, because this is 2 times the sum of cubes. Then each of these cube appears twice, x cubed plus x cubed, and then y cubed plus y cubed here, and then z cubed plus z cubed here. And then in this first solution I will use a substitution method, so I will not use x, y, and z as variables. I will let a to be equal to x cubed plus y cubed, b is y cubed plus z cubed, and c is z cubed plus x cubed. And since x, y, z non-negative, it is also the case for a, b, c to be non-negative. So substituting a, b, c to the original inequality, we get this one. It is easy to check. It looks much more simpler now. And so rewriting again, we get this inequality. We just move the right hand side to the left hand side. So we must prove that all of this on the left hand side is non-negative. And since this involves many square roots, that it might be useful for us to use the multiplication of conjugates. So let us see what I mean. We want to prove this inequality. So first I will analyze the left hand side. We try to change the left hand side such that it is clear for us that all of this is non-negative. So first I group the square root of c plus 1 with square root of a plus b plus c plus 1. We have this. And now I do multiplication by the conjugate. That is square root of a plus b plus c plus 1 plus square root of c plus 1 over the same thing. So we get here, we have here all of this. The denominator is the conjugate, and then the numerator is just square root of a plus b plus c plus 1 squared minus square root of c plus 1 squared, which is just a plus b plus c plus 1 minus c plus 1, that is a plus b. And now I want to eliminate the variable c, because it will help us to solve this problem. It will make it more easier. To do that, we can just eliminate this c, because if we eliminate the c, then the denominator is now smaller. Smaller denominator means bigger of this number, this fraction, but this is minus. So we have that all of this in total is smaller. Without the c, all of this is smaller. And now we have eliminated the c. And then again, we multiply the conjugates. Again here, a plus b over square root of a plus b plus 1 plus 1. Multiply by its conjugate to get this minus square root of a plus b plus 1 minus 1. It is easy to check because the a plus b will be cancelled, because this denominator multiplied by the conjugates becomes a plus b. And then we have here the red one, the simplified one. So we can see here that it looks similar to the original one, but without the variable c now. It only involves a and b. So we have all of this, square root of a plus 1, square root of b plus 1, square root of c plus 1 minus square root of a plus b plus c plus 1 minus 2 is bigger than or equal to all of this, involving a and b only. Okay, so we have this inequality, our result here. And now I will do the same thing again. Now I will group for the right hand side here, I will group the square root of a plus b plus 1 and square root of b plus 1. And this time we will try to eliminate the variable b. We can do that by first multiplying by conjugate to get this a over square root of a plus b plus 1 plus square root of b plus 1. That is easy to check. And we use inequality now. We can eliminate the b here because the denominator is smaller and the fraction is bigger, and minus of this fraction is more negative. So we have all of this is bigger than or equal to this form without the b. And again, we multiply by the conjugate again here. We will get only square root of a plus 1 minus 1. And all of this is exactly equal to 0. So we have done proving that all of this, square root of a plus 1, square root of b plus 1, square root of c plus 1 minus square root of a plus b plus c plus 1 minus 2 is non-negative. That is the inequality here. So this is the first solution. This is a very interesting solution by using a multiplication by conjugate and elimination of variables. Now I will start to show you the second solution here. In the second solution, it uses the Karamatha's inequality. This is Jovan Karamatha. Okay, so I will explain first what is Karamatha's inequality by first explaining what is the concave function, because Karamatha's inequality involves concave function. This is an example of concave function. In a concave function here, the curve here, if we take any 2 points and we take the straight line connecting the 2 points, then that line must lie below the curve right here. Now, if we have a function and we know that the second derivative is always negative, then we can guarantee that it is a concave function because the shape of the curve will be like this if the second derivative is negative. Okay, so and then another example of concave function here. This is more concrete. Y equals square root of x plus 1 here, because if we take any 2 points, the line will always lie below the curve. And also, we can see the second derivative is minus 1 over 4 times square root of x plus 1. It is easy to check that this second derivative is always negative. Another example here, minus square root minus x squared plus 5. It is obvious that this is concave. Okay, so now let me explain what is the Karamatha's inequality. If we have a function that is concave function on some interval I, and if the set of points on I, we have two set of points, for example, the set of points of x sorted in descending order, x1 and then x2 until xn, and also the same number of points, another set of points y with the same number as x, sorted in descending order y1, y2 up to yn, such that the set of points of x majorize the set of points of y. I will explain what majorize means later. Then we have this Karamatha's inequality. Fx1 up to plus fxn is less than or equal to fy1 up to plus fyn. Now, the majorize, we say that the set of points x majorize set of points of y if this behavior is true. That is, if x1 is bigger than or equal to y1, that is the maximum points of x is bigger than or equal to the maximum points of y. And also the x1 plus x2 is bigger than or equal to y1 plus y2, and so on, gradually, up to x1 plus up to xn is bigger than or equal to y1 plus up to yn, yn minus 1, sorry. And then also, the sum of the x points must be equal to the sum of the y points. Now, if we have this behavior, then we can say the set of points x majorizes the set of points of y. And we can use this inequality. Now, let's start to solve our problem. That is our inequality right here, written in terms of a, b, and c, the same as the first solution. We use the substitution, right? The same as the first solution here, the inequality that we want to prove, and we have a square root here, And we can use the function. Fx equals square root of x plus 1. This red one is just a rewriting of the original inequality. I will use the function square root of x plus 1, and this has second derivative is negative. And as we have seen before, this function is concave on this interval right here, x from 0 up to infinity. Okay, so and then let us take the set of points. Now with the loss of generality, since this inequality is symmetric in terms of the variables a, b, and c, so we can say with the loss of generality, a is the largest one, and then second one is b, and the smallest one is c. This is the first set of points a, b, and c, and then we can also have a plus b plus c is bigger than or equal to 0, and it is bigger than or equal to 0 too. So this is the second set of points. We can let this as y1, y2, y3, and this is x1, x2, x3. And so we have here, or maybe this is x1, x2, x3, or this is y1, y2, y3. So we have here the set of points a plus b plus c, 0, 0, majorized set of points a, b, and c. That is easy to check because a plus b plus c is bigger than a, and then a plus b plus c plus 0 is bigger than a plus b, and then the sum of the points here is the same, right? So based on the Karamatha's inequality, fa plus b plus c, and then plus f0 is less than or equal to fa plus fb plus fc. And this is exactly square root of a plus b plus c plus 1, and then plus 2 because f0 is 1. And then all of this less than or equal to square root of a plus 1, square root of b plus 1, and square root of c plus 1. And this is exactly our inequality right here. So we have proved this inequality using the Karamatha's inequality. So that's it. Those are the two solutions for this interesting inequality. Thanks for watching and see you on my next videos.